Hey everyone, today we're going to be talking about stereoisomers, particularly enantiomers, diastereomers, and meso compounds. This video is going to be an extension of chirality and R or S configuration, so if you're not fully up to speed on those concepts, please check out my previous video on those topics. To start, enantiomers are isomers, so they have the same molecular formula, but they are mirror images of each other, and they are not the same molecule. Think of your right and left hands. They are mirror images, but you cannot rotate or move one to be exactly like the other. It can be hard to tell these molecules apart because they have the same physical properties, like melting and boiling points, for example. However, they do have different optical activity. These chiral molecules rotate light that hits them, and enantiomers rotate light by the same magnitude, but in opposite directions. So one of the enantiomers will rotate it to the left a certain amount, and the other will rotate it to the right that exact same amount. Enantiomers also work or interact with other chiral molecules in different ways. Let's look at an example. I'm going to add in my implicit hydrogens. So the only chiral atom in this molecule is going to be that carbon right there because it has 4 different groups. We can assign our priorities really quickly to determine if this chiral center is R or S. To assign priorities, let's go one atom out in each direction. So we have an O, 2 C's, and an H. So we know the O is going to be first priority, the H is going to be 4th priority. I'm going to write those in. And we have a tie with the C's, so let's see what they're connected to. Each of them are connected to another carbon and 2 hydrogens. So we have a tie there, so we need to go out one more atom. Those are both, again, C's. But the one on the left is connected to an oxygen, whereas the one on the right is connected to 3 hydrogens. So we know that the one on the left is going to have second priority, and the one on the right is going to have 3rd priority. Now, the 4th priority is pointing towards us. It's on a wedge. So we're going to just look at this molecule and determine R or S as normal, but then we're going to flip it so that way we're actually figuring out the RS configuration as if the hydrogen was pointing away from us. So going from 1 to 2 to 3, it looks counterclockwise. So we think it's S, but since the hydrogen is pointing towards us instead of away from us, it's actually going to be R. So this molecule is R. Now we have to draw an enantiomer for this molecule. We have 2 options. You can either draw the mirrored version of the molecule, and I can show you what that looks like. Or you can draw the exact same molecule, just change the wedge to a dash, and if it was a dash, change it to a wedge. So I'll show you what that looks like. So these 2 molecules should be enantiomers to that first molecule. Let's check the RS configuration of the 2 chiral centers, or of the chiral center on each molecule, just to make sure. Since the configuration on the first molecule was R, both of these enantiomers should be S. So let's go ahead and denote our chiral carbons, put in our implicit hydrogen on the chiral carbon. Since we already assigned priorities for that first molecule, I'm just going to use those same priorities. Now for this top molecule, again, the hydrogen, our 4th priority group, is facing towards us. So we're going to find the RS configuration as normal, but then flip it so that way it would be like the hydrogen was pointing away from us. So this molecule, it looks like it's clockwise, so R, but it's actually going to be S. And for the second molecule, the hydrogen, the fourth priority, is pointing away from us, so we can just go ahead and look at it as normal. So this looks counterclockwise, so this is S. So these two molecules on the right side of the line, they are enantiomers to that first molecule. I wanted to bring up a point about optical activity. Each enantiomer rotates light by the same magnitude, but in opposite directions. So let's say this example, or this molecule on the left, would rotate light 50 degrees to the left, and either enantiomer, they're both the same molecule on the right side, they rotate to the right by 50 degrees. Since each enantiomer rotates light by the same magnitude, if we have a mixture of equal amounts of each enantiomer, there will be no net optical activity because these rotations will just end up canceling each other out. Such a mixture is called a racemic mixture, and it's important to note that there is no net optical activity. The reason for that, again, is that with equal amounts of each enantiomer, they each do their own optical activity, reflect and bend light in their own way, but it cancels each other out, so there is no net optical activity. Diastereomers are compounds that have multiple chiral centers, but differ in the R or S configuration around at least one, but not all chiral centers. Unlike enantiomers, which are mirror images, diastereomers have distinct physical and chemical properties. Let's go through an example. In this molecule, we have two chiral centers. They are these carbons right here. If you're unsure why, draw in your implicit hydrogens, at least on those two centers. The reason I'm drawing them on the wedge or the dash is based on the other atom. If the other atom's on a wedge, the hydrogen has to be on a dash, and if the other atom's on a dash, then the hydrogen has to be on a wedge. Let's assign the priorities and determine the R or S configuration for each chiral center. I'm not going to go too much in depth on this, but the BR is the first priority. This extension right here is second priority. The other carbon is third priority, and the hydrogen is last priority. Now, the last priority group is on a dash, so it's pointing away from us, so we can just go ahead and figure out R or S configuration. That is clockwise, so this chiral center is R. Now, for the second chiral center, get rid of this. For the second chiral center, the OH is going to be first priority. This extension is going to be second priority. The carbon is going to be third priority, and the hydrogen is fourth priority. Now the hydrogen's on a wedge, so it's coming towards us. So we'll figure out RS configuration like this, and then reverse it, so that way we get the configuration as if the hydrogen was pointing away from us. So this looks like it's going to be clockwise, or R, but it's actually S. An enantiomer would be an exact mirror image, meaning that the first chiral center would become S and the second would become R. An example of that would be this is your enantiomer. A diastereomer, in this case, would only have one of the chiral center changed. So there are two possible diastereomers. You could either change the first chiral center or the second chiral center. And with diastereomers, it's a lot easier to just switch the wedge to a dash or the dash to a wedge to flip the orientation. So for this first diastereomer, I'm going to switch the BR to a dash. but I'm going to keep the OH on its dash as well. That way I only change the orientation of the first chiral center. Now for the second diastereomer, I'm going to keep that first chiral center the same. So I'm going to put the BR on a dash, but I'm going to change the configuration for the chiral center with the OH. So I'm going to put that on a dash as well. We can go ahead and check. So for the chiral centers that we did not change, we know that they are still R and S. But let's go ahead and draw in our implicit hydrogens. Assign priorities. And go ahead and find SR or S. So this looks like it's R, but the fourth priority is on a dash, or a wedge, so it's pointing towards us, so we need to reverse it. So that chiral center is actually S, which is opposite from the original molecule. And for the second one, the fourth group is already pointing away from us, so this looks clockwise, looks R, and it is R. So that changed the conformation of the second chiral center. So in these diastereomers, in each of them, only one chiral center, not both, the configuration was changed from R to S or S to R. Meso compounds are achiral molecules that contain chiral centers. Achiral just means they're not chiral. They have a plane of symmetry that allows for an internal mirror image, meaning that if you take their mirror image, it's the exact same molecule. Since they are achiral overall, they are therefore optically inactive. This means that they do not rotate any light coming in and hitting them. They do not have enantiomers either because their mirror image is the same molecule. However, they can still have diastereomers. Here's an example. If you want to find the two chiral centers, they are these two carbons right here. Let's determine the configuration of each before we do anything else. The reason that this group gets higher priority over this group is because if you keep going down, this carbon's connected to another carbon, while this carbon is only connected to 3 hydrogens. The fourth group is going away from us, so we can go ahead and find R or S. This looks clockwise, so this is going to be R. Now for the second chiral center, the fourth group is also pointing away from us, so we can go ahead and find R or S. This looks counterclockwise, so that chiral center is S. Now, the plane of symmetry is right here. You can see on either side of that line I just drew, the molecule is the exact same. So if I try to take the mirror image or draw a diastereomer, an enantiomer, it would end up being the exact same molecule. Hence, there are no enantiomers possible, but there are 2 diastereomers. So again, to draw each diastereomer, you only change the configuration of one of the chiral centers. So for this top one, I'm going to change the configuration of the first chiral center. And for the second, I'm going to change the configuration of the second chiral center. So these two are diastereomers to the original molecule. And you can check, these two actually end up becoming enantiomers of each other. If you would like extra practice with determining R or S configuration, you can go ahead and check that these two molecules are indeed diastereomers of that initial molecule by assigning R or S to both the chiral centers. You do have to be very careful when determining a plane of symmetry. For this molecule, it might seem appealing to say that it has a plane of symmetry somewhere right there. However, that's not the case. single bonds can rotate, kind of like you're just twisting it along that line. So this bond, if you think about it, if you rotate it like that, that chlorine's coming towards you right now, but if you rotate that 180 degrees and get the bond to look something like this, that chlorine's actually going to be pointing away from you. If you have a model kit, you could try building this molecule and then twisting that bond, and you'll see how when you twist it 180 degrees, that chlorine ends up going from towards you to away from you. Now, when the molecule's like this, you can see that it doesn't have a plane of symmetry because one chlorine's on a wedge or one chlorine is on a dash. So a simple trick that I like to use when dealing with molecules that have two chiral centers is that if both chiral centers have the same configuration, it is not a meso compound. So I can show you what that looks like on this molecule. So let's go ahead and draw our implicit hydrogens. And I'm going to assign priorities. So that chiral center looks clockwise, so it has a R configuration. And for the second chiral center, I'm going to assign priorities. This one's also going clockwise, so this one also has a R configuration. Since both of these chiral centers are R, even though it looks like it might have a plane of symmetry, it does not. It is not a meso compound. I want to note, though, that the two chiral centers being different configurations, one is R, one is S, does not make it a meso compound. That is a requirement, but that compound has to have that plane of symmetry. That is the biggest thing for it to be classified as meso. It's just that if both chiral centers are the same configuration, the molecule for sure cannot be meso. Last note, if a molecule has n chiral centers, the maximum number of stereoisomers is 2 to the n. So if we have a molecule with 2 chiral centers, it will have 2 to the 2 4 stereoisomers at a maximum. Being a meso compound can make you have a lesser number, but 2 to the n is always the maximum. The reason is that each chiral center can either be R or S, giving 2 options for each chiral center, so there's 2 to the n combinations. Thank you so much for watching.